Ohio everyone, today we'll be going over linear regression. I'll split this topic into two videos. This one will cover the theory behind linear regression and the next one will go over how to code it. Linear regression is used to find a linear equation of form y equals a1 x1 an xn that best describes a set of data points where y is an output, x1 through xn are inputs, and a1 through an are the weights, which represent how much a given input will affect the output. For example, for the equation of a 2D line y equals mx plus b, a1 equals m, x1 equals x, a2 equals b, and x2 equals 1. Once this linear equation is found, we can then calculate the error in using this approximation, and if the error is within an acceptable range, we can then predict the output of new inputs fairly reasonably. For example, let's say that we have these data points plotted on a graph of how tasty a Subway sandwich is against the number of sauces in the sandwich. Here we can see that according to the data, the tastiness is related to the number of sauces as per the following equation. And assuming the resulting error is acceptable, we can now predict the tasty value of using any number of sauces. Though this example only uses two inputs, the number of sauces and 1, and their respective weights, the methods about to be discussed can be used to create the best approximations for n inputs and their respective weights. There are two different methods we can use to write a linear regression algorithm. The first method involves minimizing the sum of the squares of the errors using calculus, while the second involves using the matrix least square solution. Before we go on, note that the approximation function can be represented as a dot product between a weight vector and an input vector. This form is easier to work with when implementing the code. The error for a single data point is given by f of x minus y. Naturally, we want to achieve a total error, the sum of the errors of each data point, of 0, or as close to 0 as possible. However, since the error in this form can be negative or positive, the total error could end up as 0 when in fact we haven't reached the best approximation. For example, here we can see two linear equations that attempt to describe the same data. Both lines have an error sum of 0, but clearly we can see that the line on the right is the better approximation. To circumvent this sign issue, we will simply take the square of the errors, resulting in this formula. If we find the approximation that minimizes the sum of the square of the errors, then by extension, we also minimize the total error. For those of you familiar with calculus, you know that taking the derivative of the error function with respect to the weight vector, since that's what we're optimizing, and finding the solution such that the derivative equals 0 will minimize the error and hence yield the best approximation. We know that there is no upper bound for the error, so any solution that results in the derivative being 0 will minimize and not maximize the error. However, obtaining this error function and finding the best solution that way is very inefficient. You would need to calculate the error in using a certain configuration of weights for several of these weight configurations, and then find the configuration that results in the lowest error. If we only use two weights and only a couple points of data, it wouldn't take much time to find this error function. But if we increase the amount of data or inputs, the time will drastically increase. To overcome this issue, we can use gradient descent or stochastic gradient descent. The basic theory behind gradient descent is that if we take a particular weight vector w and take the derivative of the error with respect to the weight at that point and move in the negative direction by a step of s, we will now be closer to the vector that results in the minimum error. Let's say that our error function looks something like this, and we pick a random weight w. The derivative at this point is positive, so we must take a step proportional to the derivative to the left. We now arrive at a new weight. We repeat the same process, but because the derivative is of less magnitude, the step we take is smaller. If we continue repeating this, we will get sufficiently close to the weight that minimizes the error. One thing to note is that our step size must be of appropriate magnitude. If our step size is too large, our approximation could be unboundedly inaccurate. If it's too small, then we might never reach the minimum. To resolve this issue, we can decrease the step size through each repetition of the gradient descent algorithm. Stochastic gradient descent works off of the same principle, except it only uses a single error squared, and not the sum of all the errors squared, to determine the direction to move in each time. If the step size is small enough and if the data has some recognizable trend, then the error resulting from one data point can represent the errors of the other data points to an extent. Thus, this method will yield an approximation of about equal accuracy to one produced through gradient descent. Since gradient descent calculates the total error each iteration, for large datasets or amounts of inputs, it will be exceedingly slow. In these cases, the use of stochastic gradient descent is warranted. Although gradient descent is undoubtedly more accurate than stochastic gradient descent, the difference in accuracy is often negligible. If stochastic gradient descent does not prove to be accurate enough, or if you have a large number of inputs or a large number of data points, then a combination of gradient descent and stochastic gradient descent, known as mini-batch stochastic gradient descent, can be used, where the sum of the squares of the errors of a small batch of data is used in each iteration of the algorithm. For our purposes, using stochastic gradient descent will suffice. The second method comes from linear algebra. For a linear system AW equals B, which is just a collection of linear equations, the solution with the least error is the combination of the linear equations within A that results in the distance between AW and B being as small as possible. In other words, the factors that result in a best approximation linear equation that is as close to each linear equation A1xi1 through AMxim equals Bi as possible. The W that gives the best approximation is known as the least squares solution and is given by W equals ATA inverse times ATB. For those of you unfamiliar with linear algebra, AT is the transpose of A, and ATA inverse is the inverse of the matrix ATA. You do not need to know the specifics of how to obtain an inverse or how to transpose a matrix for this project, since we have codes or commands that can do these for us. Now that we know what the two methods are, we can now write some pseudocode, or outlines, from which we can work off of. For method 1, after declaring our step size and initial guess at a best approximating weight vector, we need to apply stochastic gradient descent for each data point, and we can repeat that whole process for an amount of our choosing. For each iteration before the stochastic gradient descent loop, we need to decrease our learning rate to obtain the approximation of highest accuracy. Lastly, we return the approximation we obtained. For method 2, we simply need to apply the aforementioned formula and return the result. Simple. As mentioned in the beginning, my next video will show how to code the linear regression algorithm. So until then, try to code it by yourself. Adios, peloelotes.